In my last video, we ended with Leibniz's visionary idea to develop a symbolic language he called the Characteristica Universalis to calculate the truth about our real world. It took about 200 more years until some new achievements raised the question again if Leibniz's dream was realistic. George Boole published in 1854 his book The Laws of Thought. His great idea was to use algebraic notation to represent logical statements. All variables in his formulas represented statements that could be either true or false. For instance, x could mean the sun is shining, while the variable z would mean we go to the theater. Boole experimented for years with an algebraic representation of logic expressed otherwise in natural language. His idea was to write 1 for true, 0 for false, and for example for the negation of a formula, to write 1 minus this formula. And there were also proposals of Boole for many other expressions in natural language like x and y, x or y, if x then y, etc., etc., by combining them to algebraic formulas, using only the symbols we have spoken about. Boole created a language that we call today the propositional logic. Another name used for this kind of logic is zero-order predicate logic, because this kind of logic does not contain predicates. What predicates are, we will be discussing in future videos. Boole's logical apparatus consisted of rules we call today axioms of his algebra. Most of the rules work pretty much the same way we learn about them at school. There are associativity, commutativity, distributivity rules, and only a few of the rules are different from what we learn at school. I marked them in red on this side. For instance, 1 plus x equals 1 in Boole's logic. Normally you would say that this formula is not a valid one, but in Boole's logic it is a valid one. The special symbols 1 and 0 have some unique properties. For instance, multiplying any formula by 0 gives us 0, a false statement, while multiplying any formula by 1 gives us the formula again. Finally, for every formula there is a negated version of it called its complement. Boole's logical apparatus clearly separated syntax and semantics. By semantics, he meant replacing all the variables by the values 1 or 0. Note that when doing so, we might come up with different interpretations of the same formula. To give you an example, let's take this formula here. In the first interpretation, we could replace x by 1, y by 0 and z by 1. When doing so and applying all the axiomatic calculation rules, we come up with the interpretation 0, which is false. In the second interpretation, when all variables are 1, we come up doing the same calculation with the interpretation of 1, which is true. So we have one formula which can be sometimes false and sometimes true, depending on the interpretation of its variables. Negating a formula to get a complementary formula relies on a rule called tertium non datur. It means in Latin, except true or false, no third thing is given. Tertium non datur creates a kind of invisible mirror in the universe of all possible formulas of Boole. As we have seen in previous examples, there are always true formulas. For example, x plus 1 minus x is always true, independently of the interpretation. We call them valid formulas or tautologies. If you negate a tautology, Tertium non datur tells you that you'll get a formula that is always false, independently of any subjective interpretation. Those formulas we call contradictions in Boolean logic. And then there is a whole spectrum of Boolean formulas that are sometimes true and sometimes false, depending on the interpretation. We call them satisfiable formulas. So the satisfiable formulas are all tautologies and all the formulas which cannot be contradictions. And only contradictions are not satisfiable. Interestingly, at least in Boolean logic, no algorithm, much better than a brute force algorithm, is known to identify tautologies and contradictions. Suppose we have a computer that can check 1 million interpretations per second for a formula. In the worst case, it has to check a huge number of interpretations, namely 2 to the power of the number of variables in the formula. So we have an exponential growth in the runtime. If we have, for example, a formula which contains only one variable, then our computer would need to calculate 2 interpretations, and with this speed it would take only 2 nanoseconds. For 10 variables, we would have already over 1,000 interpretations, which would take 1 millisecond. For 50 variables, it would already take 35 years, and for 100 variables in our formula, it would take 40 million billion years. So note that there is a fundamental difference between provability and truth in Boolean algebra and mathematics. For centuries, mathematicians believed that truth and provability were the same. As we see in Boolean logic with formulas, computers and humans can prove that 2 Boolean formulas are equivalent by transforming one formula to another, mechanically applying Boolean algebra axioms. This is about syntax, without meaning. We do not need any intelligence or artificial intelligence to accomplish this task. But then, when it comes to semantics, computers or humans cannot feasibly identify if a formula is a tautology or a contradiction. We have to try out all the interpretations that are possible to do so. So this fundamental difference between provability and truth will become even more important in future videos. Thank you. That's all, folks, for today. I hope you enjoyed this video about propositional logic and Boolean algebra, and see you next time.